Hey, it works. It's always good to see things finally starting to work. Day one of class, it's really a pot shot. And if you're curious of whether or not we're recording or not, you should see something somewhere in your Moodle, or excuse me, your Zoom controls that says meeting is now streaming live to YouTube. The downside, though, of streaming live to YouTube is I have to unshare my screen. And so any notes we put up here, it disappears when I reshare it. And this is my workaround. I'll just usually take a screenshot in case we have something we might want to take a look at again. Looks like we've got about a couple minutes. One thing we'll try to always make sure we do in class, if I forgot to say last time, is I'll be sure to always start right on the minute. So that way, if you're coming in at 2 o'clock, the only thing you might have missed is student questions or anything like that. Some of these recordings, I'm starting to realize you might have to skip ahead a few minutes. It's just going to be us sitting here waiting. I'll probably get this a little bit better nailed down so the recording starts closer to when we start. Well, it's official, folks. Looks like we can get started. Welcome back, everyone. This is some of the stuff I was talking about with another student at the start of class. Always try to keep these pasted in case other people are curious. And these are just a preview problems that we're going to be looking at really shortly. I also mentioned this a lot in class. If you have questions while we're waiting, don't hesitate to ask. But if I forget to say it or write it down, just think of that as a standing assumption. So to start us off today, anyone have any questions, comments, or concerns that they would like to begin with right away? Okay, well, let's get started then. Let me minimize this screen here. Today is still kind of a lighter day, I'd say. We might get into section 2.3, but we're not going to try to rush to get there. What we're still trying to do is introductions, getting used to the course, getting used to how the homework system is working and such. And so let's start really by going back up here and taking a look at WebAssign a little bit more. For those folks who might have just joined the class, essentially everything about this course goes through this website. I added a new link here, course materials. I think there's an email in ISU that said we need to add that to every Moodle course. But when I click on it for my view right here, this is all I see. It seems kind of broken when it loads in. Is that what folks are seeing if you've clicked on that link yet? Okay, I'm not sure if we really needed that link. I put it up here just in case we were missing something. It's definitely a lot of new stuff to figure out this semester. It's kind of impressive. Dennis says, yeah, broken in all my classes. I have one class where it's working, but that's probably because I'm using a Pearson content with something called MyStatLab. That might be the only reason it's working. Very strange. Hopefully they get things figured out for us. I'd say the good news though is I looked into this and about 80% of the class is registered as of early this morning, so even more probably about now. So good on you folks. What I'll be doing probably on maybe a Thursday or Friday is contacting folks who are not registered and see if there are any problems or things that might be preventing that we can do a workaround on. Thanks for letting me know, Douglas, as well. Looks like it's just a broken link. Very strange. Any questions, folks, about getting registered for WebAssign at the moment before we jump into there? Okay. One thing that's kind of weird about this class is I'm trying to give about 5 to 10 seconds after I ask a question because we have to deal with latency and things like that. So if you feel an uncomfortable silence, it's really just to give people time to respond. And if I don't give you enough time, you are welcome to interject. I have no problem pausing my thought and getting to your question. But if we're having no major issues getting registered in WebAssign, that's really great to hear. Let me click on this link now and let's take a closer look into the system. We didn't talk about it much last time. Let me click on sign in. Okay, looks like I do have a communication. That's pretty cool. I'll take a look at that later. I need to click on view as a student. And this now should be about what you're looking at when you're coming into WebAssign. So you'll see your assignment list somewhere around here. It might look a little bit different from you since this is supposed to be a student view, but I'm viewing it as an instructor, which changes a couple elements on this. But we're not doing anything super fancy on WebAssign. It's just going to be a place to practice homework sets. There'll be no quizzes, no exams, or anything crazy like that. So essentially everything you're doing in WebAssign is just getting through these assignments right here. So kind of the experience is either use the link here or a shortcut on your desktop, click on one of these sections and just start working. I'll talk a little bit more about WebAssign and things like due dates, but I want to mention right now, the due dates you see at the moment, they are really just in flux. If it says August 28th, then what that means is I'm thinking we might finish that section today to give you a 1 week turnaround. If it turns out we just need more time to get through section 2.2, I move that due date forward so you always have a 1 week turnaround on the due date. Any questions about any of those elements so far? Okay, well, clicking on one of these sections, here's what it looks like. It is kind of a basic system, if I'm being completely honest. You'll have your questions here. I've weighted every single question to be equal weight, and you just have a total score out of 100%. Because this is just practice, I didn't try to limit your number of attempts on any of these questions. So every one of these has something like either it's unlimited or 99 attempts on these. So it's all about practice, and it's more about knowing how you got the right answer, why it's the right answer when it comes to these problems. These kind of questions you'll see here, for the most part, are a direct correspondence to what you're going to see on the actual lecture notes down below here. Well, sounds like we have a little bit of feedback. There we go. So if I scroll down, here's a few questions we haven't quite gotten to, and you'll notice that there's some matchup with what you see here on these questions. It's not perfect. There's a couple of curveballs here and there. Say, for example, I don't think I have one directly like this one. It's one of the kind of questions you can take a look at what we did and see how it should go. But if something just looks totally bizarre, you're not even sure how to get started, you're always welcome to click this right here, ask your teacher. And I mentioned this a lot. I might reiterate a couple times in class. This sends an email directly to me. It shows you your problem, but it's never a bother. So even if you're clicking that a lot on a single assignment, don't feel as though you're bothering me or anything like that. It really is my job to come back and answer these questions. So it could be anything really kind of basic. You might say, hey, Mike, I don't think we did this in class. How do we get started? Or anything along those lines. You might just say, as opposed to all that, help. Not used to this keyboard here, help. And that's just fine as well. The more information you can give me, the more targeted or response I can give. You just click send it off and there it goes. What then happens is I get a notification in WebAssign. I'll take a look at your question and respond back. If I can't give you a good enough response because it's all going to be in text, I might say, check your ISU email, and I'll directly email you something that can be a little bit more targeted to the question. So it's not all just text. We could draw out things with math and such. So that's the purpose of that button. And I promise you, if you feel like you're using it a lot, you are not. I have had students that have used this quite often, and I never felt like I couldn't get ahead of it. So this is all about practice. I am your teacher in an online class, so I expect that for this class, folks will be using these buttons quite a lot. Even if you got an answer right and you're just kind of befuddled, why is it right? I was kind of guessing. Go ahead and ask, even if for a correct question, and I can help maybe explain what the method was, why your answer is correct, those kinds of things. But it's pretty basic again. These limits have just a numerical value. So if I put in 5, let's see if that works. Probably not. This is a guess. Click on submit answer. Tells me I'm wrong. And if I need extra help, you can click on the read it button here. This takes you directly to the online textbook. It's kind of a cool feature because it's taking you to the relevant page and paragraphs of your textbook that help talk about that particular concept. So it's taking me to section 2.2, limits of functions ad infinity. So that's kind of my all-around demonstration of how the WebAssign system works. I do have a couple things that I'm going to come back in later in the semester to talk about how to request an extension if a due date goes past due and those kinds of things. But anyone have any questions at all so far about this system? Okay, I think I might have heard something, but it was really kind of quiet. So if you have any trouble with your mic, don't hesitate to use the chat if it seems like I didn't hear your question. So that's how the WebAssign works. Let me see if I can go back. Okay, so again, this is the startup page where you see everything here. Other things you might want to know is, well, where's the book? That's probably where I should have started. Right up here, you see my ebooks. That seems like the likely suspect. They'll tell you if you are on a 2-week complimentary access or if it's considered purchased and you're all set for the course. Just click on that and away we go. Here we are in the entire textbook. It's kind of nice to having a digital textbook. If you go to section 2 here, you can just start reading this thing directly on a page-by-page, topic-by-topic basis, or click on the menu button if you need to jump to something specific in that section. Say, maybe you want to take a look at limits at infinity, or maybe just the exercises. That seems kind of weird because your exercises are already in WebAssign. But if you feel like you just want to get extra practice, this is a good source of material. One of the sample exams I give, I have multiple versions of sample exams, but one of my sample exams is just targeted exercises right out of here from the back of the book. It's nice. They give you the answers as well. And I usually assign they're not assigned. I usually put down the odd problems for that version of the practice exam so you can get a good read on if you're getting these limits correct. Okay, folks, that's again a pretty quick demonstration of WebAssign. That was about 12 minutes. Any questions or comments at all about working in the system so far? Okay, I would say after the end of class today, to be considered caught up for the course, you should be registered in WebAssign and go inside here and start making some progress on the assignment. You don't have to complete it all today. I mean, there is extra time for the due date on this, but work at a decent pace, attack it a bit at a time. And if you find that the problems are just looking really tough, there is really a good process for doing this kind of stuff. I'd say the best study process would go about like this. Let me get my tool out here one moment. Still getting used to this technology here. Okay, so I would say a step-by-step guide for studying for this course would be step 1, read the section before class. Now that sounds really, really rough, and this is not going to work for everybody, but this is considered the gold standard. You definitely want to try to read through the book yourself before you come to class, if possible. If that's impossible because your schedule's busy, I totally understand. But any bit you do reading that section, even if you're just skimming through the definitions, getting the lay of the land, it helps tremendously before you come to the lecture, which is what I would consider step 2. Step 2, attend the lecture and participate as much as possible. What I mean by that is participating is if you're using the reaction tools that come built in with Zoom, I am watching those on the right. I can see if someone puts a hand up or a thumbs up or anything like that. I would consider that participation. But participation could also just mean you're simply working along with the class. It's a good idea to have a pen out, pencil out, some paper, or if you're working digitally, a tablet out, because the more you're working the same kind of problems, writing down the steps, it's kind of amazing that that really helps with retention. The more of the senses you bring in, the more body movements and action, just simply moving the pen really helps with retention quite a lot. So I consider that participation as well. It's just kind of being present, being active, and also doing the math along with us as we go. So that'd be my step 2. And then finally, step 3, do the WebAssign problems and ask for help when needed. So this sometimes feels backwards in a lot of math classes. For a lot of math classes I remember taking as a student, sometimes I start right there on step 3. I just go right to the homework set, start working them, and the minute I get a roadblock, then I try to go back to step 1. That's not bad if that's been working out for you, but this is all about saving time. And sometimes when it comes to saving time in an online class, you will save a lot of time if you're going a little bit slower. So if you pre-read the section, the lecture is going to be easier. If you're attending and you're participating in the lecture, then down here, the homework is going to be easier. And you might find that a lot of these problem sets are really, really fast in the end if you go in this kind of process. Whereas if you try to complete section 2.2 just by diving into the homework, that could feel like a really long, grueling homework set because we're running into a lot of roadblocks, different concepts we're not as familiar with as we could be. So go with that slowly, methodically, and I think that's going to help you save a lot of time in the end. So that's my quick blurb on how I would personally study for this class or any hard math class. Well, you know what? I kind of like those steps, so let me copy these. I sometimes have the zoom control inside my screenshot, but let me try to get that. And then kind of screenshots like those, if we feel like we want to save them, let me know, and I can always just throw them in the notes. Let's put it right here. Oh, wow, that's a little too big. Let's get rid of the annotate. Okay, finally, let's go here. Oh, geez. Control C that back. I'm going to learn the lay of this keyboard eventually. This is a new laptop for me. Okay, so those were the discussions we did right here before class. This needs a title. Let's call this Studying for this class recommendations. Okay, so that's the WebAssign, some recommendations to get studying for the class. But I have a couple more announcements I want to take a look at. Any questions or comments first before we get to those other announcements? Okay, let's go back to the Moodle website. I have a ton of tabs open. Let me close some of these. So that's WebAssign. If you have any problems getting registered for it, I have some basic setup instructions here, but you can also email me, contact technical support through this website to get additional support. So here's where we left off last class. This is a PDF to tell you what problems we solved, what the solutions look like, and where we left off on. And the end of each and every week, I'll also post a brand new quiz. So this is our very first quiz of the semester. And I want to mention another thing about these things. Quizzes are kind of low stakes. It's just like WebAssign, it's additional practice, but now you're practicing problems as they would be formatted on a real exam that you'll be taking. But quizzes are graded in this kind of way. Let's put this down here. They're all going to be 10 points. I give 5 points automatically for turning it in. In essence, the quiz is halfway participation credit. So completing your quiz, handing it in to me, submitting it to me is 5 points automatically. You get the other 5 points for correct answers. I do grade on partial credit. And when I'm grading quizzes, I realize that a lot of times, this is the very first time you've seen these concepts, I'm not trying to grade them really, really roughly. It's, again, just kind of a practice run on these. So 5 points for correct answers, 5 points for turning it in. And it is a take-home quiz, so you have extra time to work on this thing. And I think one of the things we mentioned as well is there's really two components to homework. The stuff you do in WebAssign, purely practice, and this is practice as well. So if you get stuck on a quiz, it is okay for you to just directly ask me, hey, Mike, I'm not too sure what to do on this, and that would be okay. So you can ask questions on quizzes as well. So again, it's just a participation credit truly. So how does this work? I don't think we've actually opened the quiz yet. Click on the link here. We have the instructions on how to turn it in. And if you click on the PDF, it's at the very, very bottom. Here it goes, finally. And this is the quiz. So these are kind of problems that we've done before in class. I try to always assign a quiz on material that we have already covered. Excuse me. This has a first couple questions on taking limits, and then just stating the asymptotes of the function. And again, a lot of this stuff is really just based off what we did prior. So that quiz is heavily based on really just this, example one. So quizzes do come with due dates. If something happens in your life and you just get behind on these due dates here, I don't have a late policy. So, I mean, I want you to go into this class, so I will accept your work. But to stay caught up with the course, definitely try to get these quizzes done ahead of time or at the due date. This time right here is not firm, really. I mean, I don't have a late policy. I would accept it at 3:15 p.m. The only reason I put 2 p.m. there is I found if I put in 11:59 p.m., then there's suddenly a lot of encouragement to work right at midnight. So that's just more of a sensible time to put in, but it's not a firm time there. Well, any questions, folks, about opening up the quiz? Okay, there's lots of ways you can solve this quiz. You could take this file, print it out if you like, or you could just take ordinary paper and solve it on there. The way you do your quiz also kind of impacts how you're going to turn it in. So if you're using a blank sheet of paper, which is completely fine, solve the quiz on it, just put down the answers and the problem numbers, then just take a picture, scan it, and directly email it to my email address. So that's how you'll be turning in these kinds of quizzes. If you decide to print it out, same thing, just take a cell phone picture, email it to my address. But some people might be downloading the quizzes, solving them digitally, kind of like how we're doing the notes up here. If you go that route, that's perfectly fine as well. Try to convert your file to a PDF just to make sure it's at its most compatibility. And once again, email it to mikejacobson@isu.edu. So that's how the quizzes will be working in this class. We'll have a quiz every week, unless something weird happens on the schedule. Say an exam date, we might skip one. Any questions at all, folks, about WebAssign quizzes or any of that kind of stuff? Okay, let's go back to the course. That's about 23 minutes of discussing these kind of materials, but it's only week 1, so I'd say that's pretty appropriate. We left off on section 2.2, so it looks like we're now ready to jump back into there and see what's going on. What I'll need today is a calculator, and I'll be using this one right here as just a basic calculator, as well as a way to get a quick graph. You never have to use a graphing calculator in this class. This is more for me just to illustrate some of the concepts. So we left off in section 2.2. Now let's review kind of what's going on in this problem before we jump into the next bit of material. In this example right here, we were given the graph of a function. It's the plot you see in red, and that's one function with various vertical asymptotes at a couple locations. But here we set the limit as x goes to infinity of x is 1, only because when x is going to infinity, we're looking at this end of the curve right here. And we noted as x gets larger and larger and larger following that red dot, the height of it seems to get closer and closer to a height of 1. If you're allowed to get closer and closer to something, then we say the limit itself is in fact equal to 1. Same kind of idea on this one. We were taking the limit as x goes to negative infinity, and at this moment, it gets really kind of tricky. There's a lot of information here we have to read. If we're going to negative infinity on this one, that means we just care about this side of the curve. We observed that the curve, even though it's bouncing around erratically, the height of that curve is getting closer and closer to a height of 2, and that's what gave this output right here for the limit. So that's the idea of limits so far. But one major idea, which is going to turn into a shortcut for calculating limits for the right kind of functions, is the idea of a horizontal asymptote. So we'll come back to this a little bit later to show how some problems can be done a little bit faster than others. But for the moment, we're going to start calculating a few limits where there is no graph. We just have a function to take a look at. So now things are going to be done algebraically. Any questions at all, folks, on this refresher problem here? Okay, well, let's take a look. This part of the course always seems a little bit dicey at first. Suddenly, we have about 8 different properties we want to talk about with the limit laws, but here's the way you definitely want to view these. This is not necessarily a list of formulas that you're trying to memorize verbatim. This is more a list of ideas you can take for granted. You can take for granted the fact that if you take the limit of 2 functions, well, you can just break it up as the limit of one function plus the limit of another function, and a whole lot of other ideas right here. So as we go to solve the problems below, I'm going to cite these limit laws to show you where they came in, how they were used, and then we'll go from there. First, before we get started, I would say limit law number 8 is probably the more important one on this whole list, at least for the problems we're about to take a look at. So let's illustrate how that thing goes. Here's our graphing calculator. Oh, I don't want to separate that one off. Let me put that there. Now I want to illustrate this limit law right here, limit law 8. Let me zoom in on it. Oh, Dan asked, is the weekly quiz expected before Wednesday's class or Monday's class? It's due on Wednesday officially, but it doesn't have to be turned in before class. If you turn it in anytime on Wednesday, it'd be considered on time. Okay, so we are looking at, let me get this going here. Limit law number 8. It says if you take the limit of a fraction, 1 over x to the power p, that should always come out as a 0, as long as your power p is positive. So the illustration on that one could be something like this. Let's take a function, f of x equals, we want to match that format. So let's call it 1 over x. And if I leave it like that, it's implied the power on x is 1, so this qualifies. Notice the direction, though. We're going off to positive infinity to the right. So I'll make my graph more like this to convey that information. So if we follow this graph, let me zoom in a bit more. See if we can retune this. There we go. It's saying if your power here is anything positive, power on that x is a 1, simply because of this exponent law, x is always equal to x to the power of 1. So that's our power that's greater than 1. And also observe, as you go down this curve, the second coordinate is going to be the height of the curve. The first coordinate is x, and as x gets larger and larger and larger, the second coordinate is getting smaller and smaller. Right now it's at a 0.21834, but you can make that as small as you want just by making the first coordinate, 4.58, larger and larger. And that's what's being conveyed here. You want absolutely large values of x's. Let's go to the right. Out here, we're at a 0.08. You can make that even smaller by taking x to be maybe around here. Now it's a 0.06, and this game goes forever. If you're allowed to get closer and closer to a value of 0, then we say the limit is 0, and we plug that in. So that's the idea of that limit law there. And it gets wrapped up with a lot of other things we're going to be doing. Any questions, folks, with how limit law number 8 goes? Okay, let's put it in action then. First one, it says, find the limit. Correct limit notation is required for full credit. And what we mean by that is, oh, I'm on the wrong tool here. Correct limit notation means we really do need to copy down that limit statement right there. It can be a bit of a bother because it feels like a lot of copying, but we have to say what we mean and mean what we say to get these things down, or else the terminology starts to get really confusing if we're not putting in the full notation. So here's how we would start off this one. It's limit as x goes to infinity of 1 over x. Well, very first thing is we want to put it in the right format. We want it to look like x to the power p, and that's a root x, so that's incompatible with part 8 of our theorem right here. But that's okay, there's always a fix. So here's some more review. I'll be using this color pen anytime it's a comment, anytime it's extra information, or maybe review information. And this one's a review on exponent laws. So if you have square root of x, there is really an exponent that goes right here. Anyone recall what it would be?
Is it 1/2?
Good call. It's absolutely 1/2, as well in the chat. Absolutely. That's one of those little things that are kind of subtle and doesn't seem like it was even ever a big deal in an algebra class until you're looking at this right here. Suddenly we need that exponent exhibited. So let's put that in. Oh, didn't mean to scribble on it. There we go. This is the power of 1/2. Likewise, if you had the cube root of x, that would be x to the power of 1/3. If it's just a generic nth root of x, where n could be, say, 2, 3, 4, 5, or maybe 1,000, this is just x to the power of 1 over n. There's kind of an odd one out. If you write root x, there's really a 2 that goes there for the index, but by tradition, we leave it off more often than not. So back to our problem over here, we know what the root x is, so we can say this is now limit as x goes to infinity of 1 over this. Oh, let me backtrack on that. Let's use what we just produced, 1 over x to the power 1/2. So now to use the theorem, part 8 above, we're looking at this portion right here. We need to have the power simply be bigger than 0, and that's what we're looking at. We've exhibited the exponent, the power p, P equals 1/2. That's definitely greater than 0, so we're matching up with here really well. And that means this is the conclusion. As long as you have x in the denominator, the power is greater than 0, the limit is guaranteed to be 0. So this thing has altogether a limit of 0. And we're done. Really, all we had to do is find the exponent to see that the limit goes to 0 on that one. Any questions at all, folks, with that very first limit? Okay, this one's kind of a warm-up in a way. If you looked into the WebAssign, that there's harder limits that we see down. We'll take a look at those shortly. But maybe let's take a look at one more bonus problem on this one. Oh, I have to be careful on what I hit enter on. There we go. Let's suppose the problem looked like this. Let's call this one a further example. Just for the sake of comparison, let's suppose we had the limit as x goes to infinity of, how about x to the power 4? This is kind of an odd one, and some folks might know this limit right away. Any volunteers for what this limit should come out as? Dexton says infinity, and yes, absolutely. This one is just infinity altogether. The ones where we get finite numbers, something special has to happen with the algebraic form of that function. The special thing here is you had something finite in the numerator. The numerator is always 1, but in your denominator, you have something that grows larger and larger and larger, and that's what makes that come out as a limit 0. Your values are just always decreasing. But the situation is a little bit different on our further example down here. X to the power 4, well, if you thought of the graph, it looks like this. Roughly. I don't think I have the shape quite right. It's going to be a little bit more flat in this location. But if you're sending x off to infinity, the whole thing is just going up this way. And that means the whole limit itself is infinity. This is an interesting way to answer this question because there's no limit law here that really supports it, how we wrote this out. So there's going to be a couple occasions where on some of these exercises in WebAssign, you might want to think kind of outside the box by wondering, what is the graph even for this thing? If you go back to anything like this, Desmos is a good one to take a look at and just put in x power 4. Then we're dealing with a graph that looks like that. Now, this is a little bit weird because I'm using a graph to get intuition on a problem to answer a question that could be on WebAssign. If you require a graph to answer a question on a real exam, I put that graph on the exams. So don't feel like you wouldn't have the tools to do the same thing if that came back as an exam question. So that's what goes wrong with this one. But another thought is, if you're really thinking in terms of this property number h right here, you might have said, well, limit as x goes to infinity of x to the power 4 is equal to the limit as x goes to infinity of 1 over x to the power, let's put this in a color that pops out a little bit, negative 4. So this also kind of says what went wrong. The power we have is negative, but we wanted a finite value if the power is positive. So that's why this limit was damaged right here. And by the way, this is an important exponent rule itself. If you have your base in the numerator and you change sides from numerator to denominator or vice versa, denominator to numerator, the sign of the exponent always flips. So if this is a positive 4, but I took x, its base to the denominator, the new power would be negative 4. But either way you look at it, the limit is infinity, like was mentioned earlier. This is just a good way to see what went wrong. It's the negative power that gave that output. Well, that's one limit law down, limit law number 8. It turns out to be a really important one. And we'll take a look at the others as we get through the problems. Any questions first? Okay, one of the things I try to avoid for a class like this one is scrolling up and down constantly because, I mean, to me, I would get dizzy after a while. So you'll sometimes see that I'm doing something along these lines. Let me get the red dot out of the screenshot. I'll just take a screenshot occasionally, take that whole set of formulas and just walk it down with us to the next problem. So there's our limit laws. Slightly scroll down so it's not too big here. And now we have a new limit to take a look at. This one's kind of tricky because we're dealing with an entire fraction, numerator and denominator altogether. And there are huge shortcuts to this kind of problem I want to mention. So if you know the answer, good on you. You're welcome to use a fast shortcut. But first, let's take a look at how this one really can be thought of or approached. You have a limit of an entire fraction, and you have a lot of different limit laws available to you on that fraction. I want to use these two because we have pluses and minuses. I guess it's really just version 2 because of the minus. I also want to use, say, limit law 3 and limit law 6, as well as limit law 8. So a lot of things are going on with this question. And here's how it would start out. We're taking the limit as x goes to infinity of 5x minus 9 divided by 3 minus 7x. And this is the author's approach. It's a little bit longer, but I think some people like this preferred to finding the asymptotes. So we'll show how this method goes. Step 1, find the power of x in the denominator that is the highest. So we have a power right here by that 3, but that's really 3x power 0, since x to the power of 0 is 1. So more interesting to us is that x, that is the highest power there to a power of 1. And so we're using this one to start. Let me circle it a little bit better. You could divide out things involving this sign, but I usually just typically work on that x right there. So step 1 is find that power. And here's what step 2 looks like. We go limit as x goes to infinity of 5x divided by x minus 9 divided by x, all of which is divided by 3 divided by x, then minus 7x divided by x. So that's our first start. We find the power that's the highest. We take that power of x. If this was an x cubed, we would have divided by x cubed everywhere. If it's just x, we divide by x. So let me see if I can put in step 2 above this. Step 2, divide all terms by the power of x. Let's say it more grammatically, by x to the power p, where x to the power p was found in step 1. Let me put that as step 1. X to the power of 1, which is equals x, is what we used. So that's how it starts off. It seems like we took a problem that was kind of cleaned up and we made a mess out of it, especially if you know the shortcut. We'll mention that shortly. But from here on out, things start to clarify and we get through the problem pretty quickly. Any questions so far, folks, with that very first step? Okay, so it's always the denominator x that we're worried about, and we just divide that highest power that we see everywhere. Next step, let's just clean this up algebraically. This is now equal to the limit as x goes to infinity. From over here, we're just going to deal with 5 minus 9 over x on this one, no cancellation. Then down below, no cancellation on the 3 over x. And 1 cancellation here. It'll just be a -7 after we do that cancellation. Now, this is the stage where a whole bunch of stuff happens at once. Notice we have a numerator-denominator. Limit law number 6 says you can take the limit of the numerator, divide by the limit of the denominator. So if we took the limit of this whole thing, well, one thing would happen right here. We'd have to take the limit of 5, but 4 here, forgot to highlight that one, says the limit of a constant is a constant. So nothing happens to that 5. We just pass right through it. And then we take a look at this portion, 9 over x. What's helpful about that is limit law number 8 takes over. The power of x is 1. It's divided by a constant, so this goes to 0 in the limit. I'll often write out this way with a pencil tool. Goes to 0, and this is my way to convey we took the limit of this part, and that whole term got canceled out. It became a 0. Likewise, this limit operator now affects the denominator right here, the full denominator, and that was through our limit law number 6 once again. We took the limit of the numerator, limit of the denominator, but we're not writing out every single step. We're just saying visually what would happen. Constant stayed where it was, that went to a 0. But now for the denominator, that 3 over the x, we can break this up into stages and just do the 3x first. That's where this limit law is coming in. In the denominator, if you have 2 terms being subtracted, take the limit of one and then the limit of the other. And for this term, it's limit law number 8 again. That's why I considered that one to be kind of an important one to list. It's used a whole lot. That makes this go to 0. Finally, the constant of -7 is not affected by the limit at all. It just stays at -7. And so here's what happens. Some folks might see the shortcut already, and we'll mention it in just a second. We have 5 minus 0 divided by 0 minus 7. So the whole limit turned into a 5/7. I don't think I can jam that in there. Let me take some extra space. That looks bad too. Let me try one more time. Equals 5/7. So we did it, folks. That's the full process on this one. Any questions or comments on getting through it? Anyone happen to see what the shortcut was? After I fix my mistake, it looks like I forgot a negative sign. So if you're wondering how we got to 5/7, I have no idea either. Let's put in that negative sign. Equals -5/7. I'm going to leave that highlighted in yellow since that was my mistake there. Any volunteers for what the shortcut is, looking at the original function?
Would you maybe just like cancel or like get rid of any of the constant and only look at any of the numbers that have a variable?
Exactly. So that's the idea of this one. If you think back of what you did in a pre-calculus class, formerly called college algebra, we're renaming classes for some reason. This is just all about finding the horizontal asymptote of a rational function. And the reason that works is x is going to infinity. Let me scroll up for just a moment. The theorem here says the limit is L if and only if it was a horizontal asymptote. So any information you know about horizontal asymptotes allows you to go like this. Let's show how the full shortcut goes. I need a different color. Let's go with that. I would say this one has a tie. What I mean by that is the highest power of x in the numerator is a 1. Highest power of x in the denominator is also a 1. So we just grab, as you said, the 5, the -7, and there they are, 5 divided by -7. So that's just the method of using horizontal asymptotes. And if this was a real exam question, if you went all the way to that, skipped all of that algebra, I'd assume you just use the shortcut. So that is a valid approach to solving this limit. So for the further problems, I'll show the long form method if that looks like a good way to do it for you. You don't have to worry about asymptotes as much, but I'll also mention the shortcut as well. Here's our next one to take a look at. Any questions, comments, or concerns first before we give this one a try?
Yeah, I had a question.
Yeah.
I got kind of lost when if you would scroll back up just a little bit.
Oh, yeah, my bad. Sorry about that.
No, you're good.
There we
Um,
go.
yeah, when you canceled out 9 over x and 3 over x,
Yeah.
I guess I didn't notice which law that was, or if I did, I don't understand why.
Yeah, I think I kind of just pointed at it with a pointer. It was this limit law right here. Let's leave this one in the notes because that is a very good question.
Yeah, it seems like a useful one, but it says it's like 1 over p or 1 over x to the power or whatever. But
Mhm.
that's 3 over x and 9 over x, not
Oh,
1.
gotcha. So let's take a look at this right here. This is an excellent question. So lim as x goes to infinity of, let's just take one of them. How about 3 over x and look at that one really closely. So how should we work this one out? Because you are absolutely right. It does not fit this format at all. This format requires a constant of 1 in the numerator, and we've got something else. But here's the next limit law that can come into play for this situation. So if we have a 3 over x, and that constant is causing us trouble, there is something on this list that can help out. It's this one right here, limit law 3. If you have a constant times a function, the function f of x there is
Oh,
going to be the 1 over x. That constant can move out right in front of the limit operator.
okay. Yeah. I think when you pointed at that, you mentioned this when you were walking it through, but I looked at 4.
Oh, gotcha.
I see 3 now, and yeah, that makes sense. So you can pull that 3 out ahead
Yes.
and
So
leave a space holder.
exactly. So now
Yeah.
we've got this to look at. And then that's when limit law number 8 takes over. Limit law number 8 says that goes to 0.
Okay. Yeah, I'm caught up now.
Awesome. That's such a
Awesome.
good question because it also highlights what's going on right here. There's a whole algebra related to limits, and a lot of this stuff are just things you start to learn to take for granted. For example, doing the 3 over x, what people would mostly do is just say, oh, that constant can move out, so it must be 0. But if you have to say y, the y is a couple more steps like that to show. Oh, I think I missed a chat. Where does the 3 what does the 3 on the outside go in that case? Oh, it would go right here. And then this portion, oh, didn't mean to use that. I want a highlighter here. Oops, deleted too much. This portion, limit as x goes to infinity, became the 0 through limit law number 8. This is a lot of color coding on this one. So our limit here went to 0, but the 3 just kept on carrying through. It just became a 3 times 0 at the very end there.
Oh, okay. So it's a 0.
Only because of the multiplication. There's an implied multiplication right here. The limit of, oh, am I highlighting? Would be better if it included the 1 over x. That's a better targeted highlighting, is what made it come out as a times 0. So right here, it's a multiplied that's implied in that case. We often just drop that out though. Here, we had to make that a times 0, so it didn't look like the number 30. These are really excellent questions, folks. I'm really impressed because these are the tiny little details that can make this kind of calculus, taking limits, very, very foggy. So I appreciate these clarifying questions. All the questions at the moment?
Would it be the same thing if that 3 was a negative instead?
It would, yeah. So if we say did the -9 over x, or just a negative right here, it would look like, say, this. -3 goes here. The -3 is still just as good of a constant, so it would come out to right there by that limit law. And we would then get a -3 times 0 right here, getting the same output. Does that make sense to folks at the moment? Okay, so it's kind of strange how they wrote out these limit laws when you think about it, because they could have written limit law 8 to say a constant divided by x to the power p is 0. That is true. There's a constant divided by x to the power p, and this one comes out as 0. But our author left it like this because that idea can be derived from limit law 3. So all these laws also mesh together. It makes it a bit confusing when you're first learning it. But the more and more we do these problems, the more we see these are kind of like exponent laws. There is like 30 exponent laws, but in an algebra class, you're not thinking about every single one memorized verbatim. You're just thinking more along these terms. Anytime you have x power 2 over x power 5, you know that you're allowed to go 1 over x cubed, that the powers cancel. It's effectively just a subtraction. That's kind of what we're doing here. We're not trying to memorize them all verbatim. We're just seeing what can we take for granted, what algebraic properties can we use, and we'll get very familiar with them just by doing some of these faster examples. That's part of the reason for taking the long method is we're also studying the limit laws, which we would have missed out on if we took the shortcut. Any other questions or comments so far, folks? Okay, let's try another one again. These notes on the first day of class, I do try to go very carefully and slowly. I usually ask a lot of questions because starting off a calculus class means you're starting off doing something weird, taking limits. It's kind of strange. It takes a minute to get familiar. And so we'll take as much time as we need to get through this section. We'll probably be finishing it when we come back on Monday's class next week, is what I think we're going to be at. But if there are more questions, I don't have any opposition to taking more time. This is one of the more fundamental things we have to get through for calculus. But let's try this out again. Again, there's a shortcut to this, and a very, very fast shortcut. Anyone happen to know what the limit should be for part C if you took a shortcut?
Is it 0?
It is a limit of 0. Good call. So the reason for that this time is there is no tie. The power is 2 in the numerator, power of 3 in the denominator. That will always give y equals 0 for a horizontal asymptote. Let's put that down in the notes. Denominator wins. By that, I mean it has the highest power in the denominator, power 3. This implies y equals 0 is the horizontal asymptote. And therefore, let's put in our little triangle. That's our symbol to just say in conclusion, or it means therefore, limit as x goes to infinity, x squared plus 4, x cubed minus 6x plus 1 must be 0. The moment you have a horizontal asymptote, you have solved the limit. Still try it out the longer method, mostly to practice the limit laws and to give you a different approach. But I just want to emphasize, anything you know about algebra, you can leverage into this calculus class. So that's a fast way to do that one. Any questions, folks, about the shortcut method?
Can you go over that one more time? I kind of missed it.
Yeah, absolutely. So let's actually look at one above just to compare the two. On this one right here, we said there's a tie. The power of x is 1 on the numerator, power of x is 1 on the denominator. And so we just took the coefficients, 5 and -7, and brought them together. But when there is not a tie, if the denominator has a higher power, x cubed versus x squared, it's now a foregone conclusion. The limit on this thing should be 0. Does that make sense at the moment? Okay, There's another way to kind of view this as well. Let's take a look at the graphing calculator for a moment on this one. So I have a pretty built up function, but let's suppose it was just x squared divided by x power 3. Now we predicted the limit is 0 through the shortcut. Here it says x goes to infinity, so we're only concerned about the positive end of the graph. And it's got the right shape. As you move to the right, the height of the curve is getting lower and lower. I'm at a 0.1912, and we can make that as small as we like by going further to the right. But that's not our function, right? This seems like cheating. In fact, this thing would simplify. This would just be 1 over x if you simplify the whole function, and it looks pretty similar. So let's bring in the whole thing now. F of x equals x squared divided by x cubed. But what happens with that plus 4? In the long run, basically nothing. In the long run, what really matters is x squared. That's a quantity that's getting larger and larger and larger. It's as if the plus 4 is irrelevant when you're way out here and start around 8. That's now at 8 by 8, 64, and that's really tiny. What about below here? If you put a minus 6x and a plus 1, function changes a little, you might have noticed, but not by much. And that's because down here, it's all about x cubed. If you're around 7, that's 7 to the power 3, and I need a calculator for that at that point. 7 to the power 3 is already 343. Then negative 6x, that would be negative 6 times 7. So if we're right here at 7, trying to get to 7, there we go. That's kind of hard. Well, there we go. Right at 7, if you plug a 7 right here, this first term is a 343, second term is a negative 42, and the plus 1 is really, really small. The further you move to the right, the more those terms, negative 6x and plus 1, have almost no impact on the function. So really, it all mattered about the denominator. That's what made this limit go out to 0. There's more to that function, but we're more concerned about just this part right here. If there was a tie, however, x squared over x squared, well, the coefficient here is 1, the coefficient here is 1, so we should expect the limit is 1. Let's take a look. I should be getting closer and closer to a value of 1. That seems plausible. That's a 1.5, but I'd probably want more numerical evidence. Yeah, now we're getting at a 1.19 and so on. So if there's a tie, you just grab those coefficients. But the moment the power of the denominator gets higher, say power 4, now the limit becomes 0 like we're seeing in this case. So that's not the full story, but that's the story so far up to part C. Any questions so far? Okay, well, we know the limit is 0. This is the shortcut. But let's try the author's official method. If we're going to do it the way the author does, here's what he would begin with. Look only to the denominator. It's all about that denominator. Find the highest power term that you can see and grab x to that highest power. And this one, it's x cubed. I think a highlighter will do better there. You take your x cubed coming from the denominator, and we're going to divide it into every single term we see above and below. So this turns into the limit, x goes to infinity, x squared over x cubed. This step takes a little bit time to show. I think if most people were doing this, they would do the division right here, call this 1 over x. I sometimes put in a little bit of writing, extra steps, only because if you come back to these notes, you'd know what happened here. There's an actual paper trail to each of the steps. So now below it's x cubed, divide by x cubed, so that'll turn into a 1, minus 6x over x cubed. Sensing the need for a little more white space, let me zoom out a touch, plus 1 over x cubed. So that's our first step going this method. Any questions, folks, on how we got here? Okay, next thing to do is just cancel these powers. So this is our exponent laws portion of the problem. We actually do quite a lot of exponent laws, so if you feel like you might need some review material on that, don't hesitate to reach out. I have some worksheets and that kind of stuff that we could look at. I agree with Douglas. The way we're doing it right here, it's long, tedious, and the more steps I take personally, the higher the odds of making a simple mistake. So knowing information about the function, the fact that the horizontal asymptote was 0 is really, really tremendous on this problem. But some people do like this method, and that means we'll keep on going. Honestly, the bigger reason we're doing these kind of problems is just a vehicle for us to get familiar with the limit laws. We're chewing on it on every single problem we're looking at. So this one is now limit. X goes to infinity. I'm on the simplification phase. X squared over x cubed turns into a 1 over x plus 4 over x cubed. Down below, this will be a little bit faster. We'll get a 1 on this cancellation minus 6 over x squared when we cancel x over x, and then a 1 over x cubed. Then what happens next? Limit law number 8 takes effect. Every term that survived with an x in the denominator still alive, this becomes 0 in the limit. So I'll convey it this way, just an arrow saying going to 0. It's like a cancellation slash, but the arrow tells me the reason it canceled is because x goes to infinity. So it conveys us slightly more information if you decide to go that route. Above right here, that goes to 0 as well. Limit of a constant is unchanged, but the next two also go to 0 due to x is in the denominator with a positive power. So in the end of the day, this is what we've got, 0 plus 0 over 1 minus 0 plus 0. This is 0 over 1, and that means the whole limit itself is 0, like we expected. So it is quite a lot of writing to get all that out. But any questions, folks, on either getting it this way or the shortcut way?
Those canceled out to 0 because of the same laws as the last problem, right?
These right here. Yes, exactly. It's basically
Okay.
kind of like this capsule limit right here. Anything that involves a constant with a power of x that's positive in the denominator gives those cancellations. Absolutely.
Just making sure I'm following.
These are very good qualifying questions. I appreciate them. Yeah, there's so many little things that are happening that I think if we were to try to do this in one day, it would just be a disservice. It's good to go slowly and carefully with this new concept.
Question.
Yeah.
So I'm with you all the way up till you're at the last step, 0 plus 0 over 1 minus 0 plus 0. So what do we do with that 1 then? Because
It would really look about like this for that missing step. We would have had a 0 over 1 as a simplifying step, but then the whole thing's 0 once we do that last computation. Watch out for these, though. The ones that we really hate are that 1 over 0. That's going to be the undefined one. You know, that's a good thing to leave on the page here. 1 over 0 is undefined. And so is 0 over 0, by the way, but more relevant to what we were looking at. These are the good ones. Now you have a limit at value 0. If this comes up, your limit was probably infinity or negative infinity. Well, we looked at a couple cases. We had a tie. We had the denominator wins. For the next, it'll be when the numerator wins. That says...
So in this instance, the limit is actually 0. The limit is not undefined.
The limit is 0 for this one, absolutely.
Okay.
And one thing that you do have, if you're doing this as, say, a homework problem, a problem you're studying on, even a quiz problem, is you could get extra information and intuition through the calculator. Now, I wouldn't rely on this too much because our goal is to know how to do this without the use of a graphing calculator. But let's say this is a web-assigned question. If you want to be sure we've got the right thing in, you can just type in the function. f of x equals x squared plus 4 over x cubed minus 6x plus 1. It gives us a function that looks about like this, where if you go to the right, we're observing the values are getting smaller and smaller and smaller. So that gives good numerical evidence that our limit is right, although it's not a guarantee. For example, there's nothing to prevent this from settling at 0.00053. We have to do it algebraically to see why is it 0 exactly, not some weird wonky number. Any other questions at the moment, folks? Okay, let's see how we're doing on time. We go from 2 to 3:15 if I recall. How about one more problem and we'll call it a day? Does that sound right to folks? Okay, let's give this a try. That looks like it deserves a new page. Let's put it down here. Okay, we've got our limit laws in case we need them, and a brand new function. So now let's do our shortcut analysis on this one to start it off. The thing to observe about this one is this time the numerator wins. The power of x is the highest on the numerator at power 4, with meaninglessly power 2 in the denominator. So here, the numerator wins. This has no horizontal asymptote. So here's where it gets a little bit tricky. If there's no horizontal asymptote, well, we might think for a function like this one, it's either going to positive infinity or it's going to negative infinity. We have to also be careful with the direction. This one is a limit as x goes to negative infinity, whereas the last two are going to positive infinity. So there's a lot to kind of figure out on this one. Sometimes it's a bit of a pot shot. If the numerator wins, this is either positive infinity or negative infinity. Can anyone tell which one it must be, either positive or negative? I agree with Jamie. This one is positive infinity, and there's a specific reason why. When we look at the numerator, the power 4 means any number you put in there, even if it's a negative number, it's just going to come out positive. Down below, we have something that's going to be positive, plus something that's smaller, but this term absolutely is going to become humongous when x gets larger and larger negative. This one becomes irrelevant. So I would expect on this one that the limit as x goes to infinity, 2x power 4 plus 7 over x squared plus 7x should be equal to positive infinity, which I'll just write as the infinity sign. That is a lot trickier this time. It could have been positive, it could have been negative. If the function looked like this, and I'll correct this in just a moment, if it looked like, say, this instead, that's kind of hard to get right there. Oh, there we go. If I put a negative right in that location, we would have had to put a negative right here. So this one does get a little bit tricky. And I would say this is one of the cases where taking the longer set of steps is kind of well worth it. So let's give it a try and see what happens. X squared is the term that wins in this one. For the denominator, by winning, I mean it's the highest power term of x that existed in the denominator. So now we're dealing with limit. X goes to infinity. 2x power 4 divided by x squared plus 7 divided by x squared. Oh, I forgot to put that in blue. We'll just hit it with a highlighter. Then it's x squared divided by x squared here. And last, 7x divided by x squared. Once we do that, this is kind of the grunge work, kind of a bit to grind out, writing all that. But now we do the simplification, and it's pretty much on its way at this stage. X is going to negative infinity. This term becomes 2 over x squared. or excuse me, becomes 2x squared plus 7x squared. The power is higher in the numerator, so we keep the term in the numerator. Below, it's just going to be a 1 plus 7 over x. In the next part of the analysis, this one is going to get really, really large when x goes to negative infinity. But this one is going to converge to 0. The constant is unaffected, so it stays as is. This becomes 0 in the limit as well. So all that's left over is essentially that. We want to know what happens to 2x squared as x gets larger and larger negative. Well, if we're not sure, you might see some problems that come out like this in WebAssign. It might be, say, x power 3 plus x power 4. Something like this. Again, you can get some good intuition just by putting in the function. So let's put in f of x equals 2x squared. But let's also be careful. If we're going to negative infinity, we want to be on this end, sort of like that. But surely, as x gets larger and larger negative, check the second coordinate. It's just going up and through the roof. So this one happened to be, indeed, positive infinity. However, algebraically, it becomes a little bit more clear it had to be infinity because x squared is, no matter what, a positive number. This is the one time where this long set of steps is actually beneficial because now it's clear why, even though we were going to negative infinity, it had to come out positive like that. Kiana says, so that x to negative infinity is essentially the domain we work with. Yeah, absolutely. I think that's a great way to think about it. If you're heading off to negative infinity, nothing is going to matter on the positive end of the domain, and vice versa. Other questions, folks, so far?
I had a question. So,
Yeah.
where it's 2x to the exponent of 4, would it be a shortcut just to have the exponent an even number to have the same sign as the constant of the answer, or would that not work?
You said, what was the shortcut again? Sorry, I missed a bit of that.
So, if say the exponent's 4, since it's an even number, the infinity of the answer would have the same sign, positive or negative, as the constant. Would that work?
Yes, absolutely.
Or
So if that was a
okay,
negative here, that would have been a negative infinity. So yeah, you're absolutely on the right track with that.
and if the exponent was like 3 or 5, then it would have been negative instead.
If the exponent was 3 here, yes,
Yeah,
because if the exponent was 3, now you're dealing with an odd function. And you have this kind of situation to deal with. Now it's heading towards negative infinity if that happened to have been x cubed. Good call. A lot of this is just being familiar with the algebra and the graphs of these kind of power functions that you see right here. And Dana asks, why does the 2x squared become infinity? If x squared is a positive number, why is it infinity? Oh, that's a great question as well. Essentially, what's happening with that x squared here is that as x moves further and further to the left, your numbers get larger. But because there is no limit to how big this is, it's 5.17, move a little bit further to the left, and now it's up to 6. There's no ending to that. It just gets larger and larger and larger. And that's what made it become an infinity altogether there. Well, it looks like we ran out of class time. You shouldn't ever feel like you have to stay after when it gets right to 3:15. And it looks like we're a minute over already. But I do take questions, so sometimes we might run over just because of the last questions of the day. But this is where we're going to leave off on today. When we come back next class, we'll take a look at a couple more limits and a couple quick applications. So I would say, as far as WebAssign goes, we're all set to do every single problem except for the very last one, which is based off this right here. Well, have a great weekend, folks. If you have any questions, I'm going to be back on Zoom at 3:30 for office hours, and I'll also be available throughout the week, so don't hesitate to reach out. You bet. Have a great one, folks.
Okay, I do have a question.
Sure.
Okay, so I just need to like reiterate this for D there. So if the exponent is odd, then the limit is going to be negative infinity.
Well, it just depends on the direction right here. So let me pull up that graph once more. Let's make an odd exponent. But let's suppose that limit right here, what if that was a positive infinity? That means x is going to the right and the values are getting larger and larger.
Okay.
But if it was a negative infinity, that means we care about this side of the graph going to the left and the values were getting smaller and smaller for that odd exponent.
Okay.
Does that make sense for 2x cubed, say?
Yes.
Awesome. There's a lot of little details to keep track of on these kinds of things. I appreciate your questions.
And say there was, I know we already did this, but so say there was a negative in front of that, like a
Right,
negative,
say here.
yes, then we would be headed into the negative direction. So it'd be negative.
Yes,
infinity.
absolutely. Yeah. One way to think about it is if it was a negative here, then it says you're putting in negative numbers, but they're getting squared, forcing them to be positive. But then you're multiplying that positive number by a -2. That would force negative infinity right here. You're correct.
Okay. And then last question.
Mhm.
If the numerator wins, we have no horizontal asymptote. But if the
Correct.
denominator does, then we do.
Yes. So
Oh.
if the denominator wins, you're always going to get a limit of 0. And this is the one where there's a tie. In that case, let me zoom out a bit. We just pulled the coefficient from here, and brought them together like that.
Okay.
So those are the 3 big cases that you would see.
Okay. And to determine that, do we just look at like do we look at the exponents or?
Right, it's the exponents on this. So this
Okay.
one's a type because it's exponent 1, exponent 1.
Okay.
Here we said denominator wins because the highest was 2 and the highest below was 3 and so on.
Gotcha. Okay, perfect. Thank you.
Yep, absolutely.
Wait, so if there's a tie, it's going to be a finite number, and if there's a winner, it's not a finite number?
Well, it depends on which one wins. Here the denominator won and it was a finite number of 0.
Right.
But over here the numerator won and this is the one that became infinity.
So if denominator is greater, it's always 0. And
Yes,
if
absolutely.
numerator is greater, then it's always it's either positive or negative infinity.
Yeah, these are the tricky ones. So these are the ones where we would almost pretty much need extra support to be really sure. And that means it's probably not going to be a really great exam question. But these are the ones where we can determine very quickly and rapidly, like you were saying, denominator wins, always gives you a limit of 0 there. Well, I'm going to head off for a minute just to take a quick break, folks. If you have any further questions, I'll be back on Zoom at 3:30. See you folks later.
Thank you.
Yep, have a good one.